If you still feel a little bit shaky on confidence intervals on proportions, this would be the time to exit out of this video, go back, rework some of those problems, rewatch some of those videos, work some of the supplemental problems that are provided for you, and extra sets of notes or in the textbook, because things are going to get different going forward, and I want to make sure that you keep them straight. Okay, so if that applies to you, go ahead and stop this video, go back and do that. If not, we're going to jump forward here and we're going to talk about a brand new distribution. It is called the student's t-distribution. We don't typically use the adjective students. That's just its proper name. We'll just refer to it as the t-distribution going forward. It is a normal distribution centered at 0 with a standard deviation larger than 1. And so the first part of that definition sounds very similar to a z-distribution, right? Because a z-distribution is a normal distribution. It has a mean of 0 and it has a standard deviation of 1. So a t-distribution, also normal, also mu of 0, but its standard deviation is larger than 1. And so right off the bat, I want to point out something. There is one z-distribution, because when I specify the shape, center, and spread of a distribution, those are all of the unique identifiable characteristics of that distribution. So when we say a normal distribution with a mean of 0 and a standard deviation of 1, there's only one that fits that description. It's the z-distribution. And further, I could say a normal distribution with a mean of 5 and a standard deviation of 7. There's only one of those two, right? When I specify all three, there's only one that looks like that. That one just doesn't have a name, right? The one that's normal, mu of 0, standard deviation of 1, has a name, and that's the z-distribution. So notice when we talk about a t-distribution, it's a normal distribution with a mu of 0 and a standard deviation larger than 1. How many numbers can you think of that are larger than 1? Right? I don't know how many you specifically can think of, but the answer is there are an infinite number of numbers larger than 1, because notice I didn't say it had to even be a whole number, right? We could have a standard deviation of 1.2, 1.5, 2, 7, 8, 8.5. There are an infinite number of options. So when we say student's t-distribution, we actually are talking about a class of distributions in general, and we need to have some specific identifying characteristic that tells us which one of the t's we're talking about, because there's a lot of options that are numbers larger than 1, right? And then I have a note here, we use these when we have data from a population with an unknown standard deviation. I want to make sure we understand what that says right there. This is very, very important. When we were working confidence intervals in the previous section, we knew what the population standard deviation was. We derived that in the previous chapter with all of that messy work that we went through about what's the standard deviation of the binomial and how we did the x divided by n, all that stuff that got really wonky in there, right? We knew what the standard deviation was, because when we work a proportion problem, right, the core of that is that it comes from a binomial distribution, and a binomial distribution doesn't have a set apart mean and standard deviation like the normal does, right? I want to make sure we understand that. If you didn't previously, a binomial distribution has n and p. Those are its parameters. Now, we use n and p to tell us what the mean and the standard deviation are. But it doesn't have a like, oh, this is the mean by itself, like the mean is 7 and the standard deviation is 12, right? We have an n and a p, and then we use those to find the mean and the standard deviation. The normal distribution is different. The normal distribution doesn't have like an a and a b, and then we use those to calculate the mean and the standard deviation, right? The mean and the standard deviation are independent in the normal distribution. You can have whatever mean you have, and you have whatever standard deviation you have, and they're just two separate ideas. And I hope that makes sense to you, because when you think about the problems we've worked in chapter 7 with means, and even some of the problems before, you can kind of get this idea. The problem had to tell you what the mean of the distribution was and what the standard deviation was. There was no way to get one from the other. I hope that makes sense, that idea right there. There was no way to infer one from the other. It was the mean was whatever it was and the standard deviation was whatever it was. But when we talk about the binomial, it's really all about what n and p are. And if I know what n and p are, I know both the mean and the standard deviation. They're related because they use the same variables, right? So they are dependent on each other. And so when we did confidence interval problems on proportions, we knew what the standard deviation was because we just followed the n and p formula that we had before, okay? And so because we knew what the standard deviation was, we could standardize and we could use our z-table. But when we deal with problems that have unknown standard deviations, we have to use a t-distribution. You say, wait, what does that mean, right? So I'm hoping so far that you may not have the full picture yet, but I'm hoping so far with everything I've said, you're at least tracking. You're like, okay, I get what you're saying. I don't know why. I don't know where it's going, but I get what we're saying. If not, go back and try to listen again, and hopefully you understand what I'm getting at with that. Because now I want to talk about the fact that because the mean and the standard deviation are independent in a normal distribution setting, when we say um, something has a normal distribution, oh, that tells us X bar has a normal distribution, we can work an X bar type problem, we had to be given mu and sigma, right? If you remember back to the problems in chapter 7, we had to be given mu and we had to be given sigma. And now that we're into confidence intervals, though, if you recall from the previous section, we said the whole point of doing a confidence interval is I don't know what the parameter is. So I'm going to take a sample. I'm going to use the statistics from that sample to make an inference, right? The whole point of the previous section was I don't know what P is, but I could take a sample. I could get a P hat and an N from that. I can build a confidence interval. And the whole point of the confidence interval is I think that P falls somewhere in that interval. And that's what we're going to do here, right? We're setting up for mean problems. So same logic, nothing tricky. We don't know what mu is. So what are we going to do? We're going to take a sample and we're going to get an X bar and we're going to use that to build an interval. And I think mu falls somewhere in there, right? But here's the catch. Notice I don't know what mu is. And so in almost all of our cases, because we don't know what mu is, we are not going to know what sigma is. I want to make sure that sinks in. Because we don't know what mu is, we likely won't know what sigma is. And you say, well, why is that? If you want, you can turn back to your notes into chapter 2. We defined what the population standard deviation, we gave a formula for that. And if you notice, one of the pieces in that formula was mu. In order to get sigma, you have to know mu. So just stop and think about that logically. Just kind of shake your head around, clear your head a little bit, and say, now how in the world am I going to know sigma if part of the formula for sigma has mu if I don't know mu? So that seems pretty hard to do, right? And then you'd say, okay, well, what if I knew mu? If I knew mu, I could get sigma, right? Okay, but if you knew mu, why are you doing a confidence interval? Right, and that's what I want to make sure you're understanding what we're doing and why we're doing this. The whole point of this is we don't know what mu is. If I know what mu is, I don't need a confidence interval, right? And there are cases where that's true because mu is just a mean on a population. I can define the population however it's needed, right? The population might be all students at this university. I can get some parameters for that because we have data on everyone that's a student at this university. I can get a mu. It might be a little hard. I might have to go through a lot of data, but I could do it, right? So if I were to be interested in some metric that was a mean on students at this university, I could go get that. I could get the actual mu, and I would never do a confidence interval because a confidence interval, the whole point is I don't know what mu is. I think it's somewhere in this range. If I know what it is, why am I doing that? I hope that makes sense. Right, so the whole point of this, the whole point of what we're talking about, the point I want to try to hammer home here is if you're working a problem on means, we will almost assuredly not know what sigma is. If we don't know what sigma is, we cannot use a z-distribution, we have to use a t-distribution. This did not apply in proportion problems because we knew what the standard deviation was because of the way the binomial works and how those formulas play into each other. So you can kind of shorten all that down to, if you have a proportion problem, you can use a z. If you have a mean problem, you almost assuredly won't know sigma. Instead, what we'll use is s, because s is the best point estimate for sigma, right? When we talked about point estimate, we just said it's basically the best guess at a parameter. Well, if I don't know the population standard deviation, my best guess would be the sample standard deviation, right? So we're not going to have sigma, we're going to use s instead, and because of that, we have to use the t-distribution. And one more thing before we wrap up, move on. I know I've talked a lot on this one definition, because you may be asking yourself why, right? Why? I'm still going to be standardizing. Why can't I go to a z-table in this case? Why does it matter if I know sigma or if I use s instead, right? And the answer to that takes us back to last chapter when we talked about law of large numbers. Remember, the law of large numbers said as my sample size increases, the statistics that I use to estimate my parameters get better and better. But notice we're estimating. We don't really know, right? And so what we're going to be doing is we're going to be using S as an estimate for sigma. We'd rather have sigma. If we can have sigma, we get to use a Z. But the law of large numbers says as my sample size gets bigger and bigger, S becomes a better and better estimate of sigma. But it's just an estimate. And so the idea that I want to get across to you is that by using S instead of sigma, we have extra variability because it's an estimate and it may not be right. And so if it's not right, what that means is there's a little bit more uncertainty. And because there's more uncertainty, I need my confidence interval to be a little bit wider. Why do I need it to be wider, you ask? And I would say, well, remember, when we say 95% confidence, what we're saying is that most of the time this process works. That if I were to do this 100 times, 95 times, it would work. If I don't account for the variability that happens by using S instead of sigma, when I build that same interval, it's not going to be right 95 times out of 100. Let's pretend I actually go do it 100 times. It actually only be right like 90 times or 91 or 89 or something like that. We have to make that interval a little bit wider so it can capture the truth the number of times we say it will. And so I want to make sure we understand that. We have to use a T instead of a Z when we use S instead of sigma, because by estimating sigma, we're adding in variability, and I need a different critical value to make my confidence interval wider so that it does capture the parameter the number of times we say it will, right? That's the whole point of a confidence interval is I've got this range of values and I think it's going to capture the parameter most of the time. If my interval's not wide enough, it won't actually do what it says. I don't want it to be wider, but it needs to be wide enough to actually capture it the right number of times. Okay, and so the idea here, A, as I mentioned, anytime we are doing a means problem and we don't have sigma, so we're using S, we will need to use a T instead of a Z. Second idea, what effect is that going to have? All of our T critical values are larger than our Z critical values because of that uncertainty that goes with the, this value may not be very good. I need to artificially kind of increase my confidence interval width a little bit. And that's what that T critical value is going to be. It's going to be a little bit bigger and it's going to account for that uncertainty and make my interval then actually capture the parameter the correct number of times. And so we mentioned there are an infinite number of T distributions. How do we know which one's which? We do that with this concept of degrees of freedom. Now, degrees of freedom is a relatively important concept. However, the definition is very helpful. So I have the definition written out for you just so you have it. If you want to spend some time with that, wrap your brain around it, you can, but it's not a definition I will ask you about. The degrees of freedom for the T distribution in these one sample mean problems is going to be equal to n minus 1. So anytime we are working a mean problem and we say we don't have sigma, we have to use S instead, oh, that means we got to use a T. Which T? Because there's a lot of them out there. How do I know which T to use? I use the T with the degrees of freedom equal to n minus 1. Now, I'm going to explain the n minus 1 because some of you may be saying, why? You do not need to know this. So if you don't want to be confused by this, that's no problem. You don't need to know this. I just want to give an explanation for those of you out here who may be saying, well, why n minus 1? And it goes to the definition. The definition is the number of sample observations that can vary after certain restrictions have been imposed. It's the idea of how many things can change once I've locked in certain things. What I mean by that is this. If I were to say we have a data of 5 observations, but I know what the mean is. Okay, I know what the mean is. So I have 5 observations and I know what the mean is. Let's say the mean is 4.5. 4 of those observations can be literally any number you want. And the 5th one is then forced to be something to get to a mean of 4.5. And try that if you want. Try that. Pause the video right now if you want and try that and try it and come up with 4 numbers. Pick 4 numbers as big or as small, as negative as decimal, doesn't matter. Pick 4 numbers as whatever you want. There is a 5th number that exists that will get you back to an average of 4.5, and there's only one of them. There's only one of them. There's not multiple numbers that will do that. And so if I were to pick my numbers 0, 1, 2, and 3, right, that those add up to 6. And I would say, well, what's the fourth number that would add up and work for me? The answer is 16.5, right? Because if I do 0 plus 1 plus 2 plus 3 plus 16.5, and I divide that by 5, I get a mean of 4.5. 16.5 is the only number that will work there. Try anything else and you will get a different mean. And so the answer is, how many things could be whatever they wanted? Well, if I have 5 data values, 4 of them could be whatever they wanted. But since I knew what the mean was, that fifth one couldn't be whatever it wanted. So our degrees of freedom are equal to n minus 1, because it's saying in these problems, if we're working on the mean, and we're trying to find what the mean is whatever it is, right? The number of things that could be whatever they want in that sample is equal to 1 minus how many things we have in the sample, because that last number has to get us back to whatever we already know the mean is. Right. So again, that's something you don't have to know. That's just kind of if you're curious. If you're not curious, no worries, you will not be tested on that whatsoever.